Okay, thank you very much. So this is the title and the authors. Okay, and this is the outline. So DME is based on an exponential map. That is the way to exponentiate a vector with a matrix. We have a square matrix, A, and then we can exponentiate the formula that is here. And immediately one get that the composition on exponential is just given by the exponential of the product, and this gives immediately the next result is that if the matrix of exponents is invertible, that means then the exponential map is also invertible, given by is an exponential given by the inverse, and this is the main result that we use for the to build it DME. Then DME, as I say, is based in exponential. There is two versions. The first version was presented to the NIST competition in 2017, and then it was based in two exponential in two different fields, FQ square and FQ to the M. And it was for M equal 3. And it was presented, as I say, in 2017. And it was broken by my co-worker, Avendaño and Marco, in 2020. But in the case, this attack only worked but in the case M odd. And also there was in the PQ forum list, a proposal of attack using the polynomial state by Bayes descent and then some decomposition. This was proposed by Beulen. It didn't work, but I will give more detail to the end. Okay, but this decomposition, possible Bayes descent attack, decided us to change the design and then to get more exponential. So the new DME, we still call it DME, but it has a different setup. This is the one who presented to the NIST, the current NIST signature competition. The main difference are the number of exponential is greater than 2. Also, there is a procedure to reduce the number of monomial. This is essential. And the other two differences also is that in the linear part we have some translation. That means that in principle there can be failure of decryptation, but and also that the exponent matrices are not public. Okay. With the setting is, as I say, now we have the public key will be a map from FQ to the N to FQ to the N, and Q is power of 2, and we denotate these parameters like that. R and Q. R is the number of exponential that we will say the number of rounds. We will see why immediately. And N is the number of variables. In fact, I just give a brief description in the case N equal 8. That is what we are using in our NIST proposal. We use a fix an isomorphism between FQ to the power 2 and the field FQ squared, where this is fixed with a base, and we call phi. And also, all the time with this, use phi bar, this isomorphism between FQ8 and FQ squared to the 4. Okay? And as I say, we have for R exponential, we will have R plus 1 linear isomorphism with translation and R exponential. So the scheme is like that. You see, every horizontal line is around. And basically, there is one in every horizontal line, there will be one linear isomorphism and one exponential. Okay? With this setting, okay. Then we will see how to, also the setting is that we have 4x4 matrix, but there will be only one or two in every row, only one or two non-zero entries, and that will be power of 2, but not power of q. This is important. Okay. Then, all right. Another important thing is that, in principle, the number of monomial increase very quickly with the rounds. So, for instance, if there is in every row two non-zero entries, then the number of monomial is 2 to the 2 to the 3 to the r. That means that basically only for r equal 3 it will give a rational number. I mean, in fact, that's why we use this reduction algorithm. This is very important. The reduction algorithm will allow us to have more than 3 rounds, even 4 or 5, and even if possible, until 6, with a rational amount of. Okay, those are just a few comments about how to get the public key. They are the polynomials. And we have a very efficient algorithm using conical product of matrices. We have this in every step. We have, sorry that I cannot, we have here this, and we present the polynomial in FQ squared in a matrix way. So this is M is a matrix of monomial, is a vector matrix. This is the coefficient of matrix of coefficient, and this is the base. And then when we multiply, I mean, two exponents in every line, we will have that, and using the Mises property of Kronecker, we get that the monomial are just the Kronecker product of these two monomial matrices, and also for the coefficient is also the same. So this gives really a very, very efficient algorithm to compute the. Okay. So, but as I said, the main point is the reduction of monomial. This can be done. There is an algorithm, a procedure to reduce the monomial, and this can be done, of course, if you have two exponents in a row. If you have only one, there is no need. There will be the same number of monomials. And the algorithm works if you have one in the two components that you are going to multiply, you get one common variable. And then you have here, for instance, this is in one monomial, we use x1, this is in the other monomial, and then for the product, you will get something like that. By the way, here is a mistake. This is 2 to the e1, okay? And then you just force, this is a very algorithmic, force this exponent to be equal to this one. This is with this condition and the linear condition, and this produce one common, the two monomials are equal. In fact, not only two monomials are equal, there will be many of them. And we will call this a collision of monomials. Okay? I put here one example with n equal 6 and 3 matrices. And then, if we don't have this reduction of monomials, the number of exponents will be 2 to the 7, 2 to the 7, 2 to the 6. But with this algorithm, we make the reduction twice. We pass to 32, 36, 24. Okay? So you see a big reduction. All right. So with this, with this setting, the core map is a permutation. So it's a one-way permutation. If we don't have, if we don't use translation. Okay. But in the current version, we also use translation. That means that, for instance, for KEM, there will be failure of decryptation, and for signature, there will be invalid signature. But in the case of signature, it's very easy to avoid this. Okay, and then continue with the setting. We have a one-way permutation. We can what we did is essentially some RSA-like scheme, and that for that we have a permutation. So we use the well-known padding standard for RSA, OAEP for KEM, and PSS for signature, whose security is well known, provide, of course, that the core permutation is secure. Okay? And as I say, a comment, we present the signature for the current concourse, but let's say that for the signature, invalid signature are very easy to avoid, because we have just to sign, we have to compute f-1 of the padding of the message, the PSS padding of the message. But for f-1, we have to compute li-1 and the exponential, and the linear are the ones who can produce some zero at some moment, and this gives invalids. But this can avoid just because we are just sequential computing all the linear maps. So if at some moment we get some zero, then we start again with a new padding. So there is no failure, invalid signature. Okay. So for security, I will mention. So far the possible attack that we can imagine. There is governor-based attack, also well descent and structural cryptanalysis. Well, let's say that we have several settings. The setting is, we just, what we call the setting, the main part is what we call the skeleton matrix, what we call configuration matrix. The skeleton matrix is just the matrix for the exponential, but in which we just substitute the non-zero exponential phi1. And this one skeleton matrix gives a lot of information. For instance, we call it E star I. For the product of this, we consider E star the product of all the matrices, those exponential matrix. Then we call TK. TK is the sum of each row. Then the number of exponents is 2 to the TK, and also the degree of the polynomial grade obtained by grade wave descent is just the TK. So in this example, then the degree of the polynomial over F2 will be 7, 7, and 6. And I say this is the main setting, and we have, in fact, we don't have all the configuration matrix that we use. Of course, we check that at least they are secure, but we don't have, let's say, an optimal configuration of matrix. That depends on the, okay. And then for the security, a few more words. With respect to grounded basis, we have to have this standard ideal, and we have to at least to estimate the degree of the complexity. We have this well-known formula for an upper bound for the complexity using F5 of 4, and where SDI is the solving degree of I. Of course, the solving degree is higher than the degree of the original base. And in the original base, we have really this very big exponent. That means this upper bound will be a very big security margin. Of course, we don't know if this upper bound is how to say strict or no. We have make a lot of experimental work. It seems yes, but let's say that this experimental work can only be done for very, very small base field. For instance, we have a computer with half a terabyte, and we can solve this this grounded basis only for 2 to the 4. So this is far away from 2 to 64. So maybe with a few terabytes we can get 2 to the 5 or something like that. But you know, we need more experimental work. So the other problem is the structural cryptanalysis. Here, the thing that we can find is that after every exponential is a quadratic map. So there is some, I would say, we have some implicit equation between the result of every round before the linear. So that means this can be used to compute the linear in a sequential way. So, for instance, we can try to compute the last linear and then go on. And the way we get this implicit equation, the output of the exponential is explained here. But also, let's mention that this reduction of I have no time to explain more, but you can, the details we have in the preprint. The reduction of algorithm also make that many monomials coincide. That means that, and then the coefficient of the monomial will be the sum of all the coefficients. That means that will make also find this implicit equation between the image more difficult. This was also one of the reasons to get the reduction algorithm. Okay, and also even if we get this implicit equation, they will be homogeneous, and that means that any solution will be until a constant, and then so you have to choose between 4 constants that gives you reasonable security parameters. Okay, so let's also all right, and then for the Veil descent, remember just this is. Just getting just a base of FQ over F2, and then with a base you get you can translate your polynomials in polynomial F2 over F2 squared. Okay, and in fact what the attack that Veil proposed was to use the Fourier-Perret decomposition algorithm that you have two generic quadratic polynomial you compose, and you get a quartic polynomial, and there is an algorithm to get the original composer, but this only works for generic polynomials. It doesn't work for the special polynomial. We saw this in the old DME, and in principle, it seems that there is no problem with that. But in any case, we can of course, with more rounds, the degree of the Veil descent polynomial are higher, and I mean this algorithm is even more complex. Let's mention that in fact the reduction of monomial algorithm also reduce the degree of the polynomial obtained by Veil descent. For instance, in the example I show you, the original degree was 776, and after reduction of monomial we get 565. But I say we can just raise this. Okay, so we were just finishing. So, as I mentioned, we have really several configuration matrices, and we have in our web page we have the implementation for some of them, and here this corresponds to the implementation that we present in the preceding paper, and as you can see, maybe I don't see well, but you will see it, that we can compare the DME signature is very efficient. So you can see here, compared with the finalist, really very efficient, and especially you see the most, interesting parameter is just the signature size is, signature size is just 64. Okay, but you can compare here, and we put also here the comparison of the one instance with four rounds and one from 3 rounds. You see the difference, the sizes, the difference of sizes and time, but you see it's very efficient. This is for the number of rounds. For the for the base field, in the proposal that we present to the NIST, we have three parameter set. In fact, you see for security level 1, 3, and 5, and you see the security level is just proportional to the size of the field. So here we have, these are the how to compare the sizes of the field. Again, they are really very effective. Okay, but you see that how change the speed with proportional to the size of the field. In fact, we'll say that in principle the implementation is very efficient. Martín did a very good job, but there is a room to improve, especially for in the you can understand from this number in the implementation of the multiplication in the big field. So there is some room for improvement in the especially the more costly step is just the inversion in the big field. So there is okay. So you can compare, and just a final word that we say. You see this is very efficient, but I have to mention that we need that you people try to check the security. So we are a very small field, and as far as we know, this verify the security that we are just claiming, but more cryptanalysis work is needed. But let me finish with one comment that even if there is, we have to make some attack will do something, there is, because of this very efficient number, there is room for improvement. For instance, we have some concern about ground net basis. Then the solution is just to increase the size. You see that the security is proportional to the size, and this it needed a very easy solution. And the same happens for some whale descent attack. If there is some attack, way to improve it is that just to increase the number of rounds. So, as I say, 5 rounds will be still efficient, even 6, but I don't think the 6 rounds they are really needed. And finally, for the structural cryptanalysis, of course, this is the more. We try everything we imagine, but here we need really that people attack it. But here also there is a good solution. That's to use the original Samir idea in when they proposed this birational signature scheme is just to erase one of the component of the public key. So this really, as far as we know, this prevent all the attack that we have come up with, and they will make, in principle, more secure the signature scheme. But as I say, as far as we get, the scheme that we present to the NIST, in principle, fulfill the security parameters. But as I say, there is room for improvement of the security. So, and that's all. Thank you very much. Sure.
Take this. All right, so what questions do we have? We have the 2 microphones. All right, while people are thinking, I have a question for you. So you mentioned in the beginning that there is the possibility for decryption failures.
Yes.
About how often is that happening?
This is, it was about 1 over Q squared.
1 over Q squared?
Yeah, yes.
Okay.
That the size of the big field. Yes.
Okay, perfect. Good. What other questions do? Oh, yes.
But here we present only the signature case that has not.
Oh, yes, yes, of course.
So you mentioned considering wild descent for this attack that came out in
Yes.
when was it? Maybe 2017,
Yes.
2018. Now, for that, the analysis was going all the way down to the prime field. Have you, and in the paper, if I remember, I think you analyzed it like considering the prime field. Would it be reasonable, and have you looked at descent where you stop somewhere else, some intermediate field?
Yes, it will be reasonable, but we did not check. So, but it's, of course, it's maybe something that we have to check.
Oh, okay,
Yes.
thank you.
Good. Any other questions? All right, let's go ahead and thank our speaker one more time. Thank you so much.